Section 9.3. Now we basically practice more about solving differential equations using the separable method, where we separated the x's and the y's and then we integrate both sides. And from there our goal is to solve for y. In some cases, when you solve for y, or you get to the point where you finish solving the equation, it might be difficult to actually get y by itself. But at least you get the equation with no derivatives at the end. So what is a separable equation or separable method? We define as a definition a separable differential equation. It's a first order differential equation. In which dy dx can be factored as a function of x times a function of y. So what I'm talking about, when we say y prime, well, you know it can be written using Leibniz notation as dy dx. So say this is given to us as f of x times g of y. So notice what I said. By definition, dy dx can be factored, like written as a product of f of x, a function in x, and a function in y, f of x and g of y. And then from here we can do the separation. So dy over g of y equals f of x dx. And to solve this, then we integrate both sides, as we did in the previous section. And to reinforce this, we just need to solve some differential equations based on a given condition. Solve y prime equals, say, x squared over y squared. Then find what we call the particular solution. Y of 0 equals 2. So here we rewrite y prime as dy dx, x squared over y squared. Then we do separable, y squared dy equals x squared dx. Integrate both sides. Look how easy this stuff is. We got y to the third over 3 equals x to the third over 3 plus c. And if you like, for fun, put over 3. It's fine. And then from there we can solve for y. First multiply everything by 3. And you can leave it here, or you can do cubic root. Let's look at a more difficult example. Say 8x squared over 5y minus 6 sine y. Still looks easy. So this one, again, we can do separable. 5y minus 6 sine y dy equals 8x squared dx. And then we can integrate both sides. Then we have 5y squared over 2 minus integral of sine is negative cosine equals 8x cubed over 3 plus c. You can either multiply everything out or just leave it by 6 or leave it there. How about another one? dy d theta e to the y sine squared theta over y secant theta. So that was, yeah, so dy d theta, no x, could be theta, could be any variable. So to do the separation, we bring the y on this side and the ey down, keep the sine squared theta over secant theta as they are d theta. So to solve something like this on the left side, we expect to bring the e to the y up becomes negative, and then on the side, you know, we know that secant is 1 over cosine, so that becomes cosine theta sine squared theta d theta. Then we integrate both sides. Y e negative y dy equals integral sine squared theta cosine theta d theta. When I look at the left hand side, it's easy to integrate. We can do u sub, u equals sine theta, and du is cosine theta d theta. Easy. But the left hand side is not easy. U sub doesn't work. We have to try by parts. We have to try by parts. So we take u to be the y, du is dy, and whatever's left is our dv. So then v is negative e negative y. And then we do uv, so negative y e negative y minus the integral of v, which becomes positive, uv minus the integral of v du equals the other side. When we did it's going to be u squared du, which is u to the third, so sine cubed theta over 3 plus c. We can finish this by integrating this one once again and keep this the same. Notice how difficult it is to solve for the y there on the left side. But at least we use integration by parts. Another one, let's say dz dt plus e to the t plus z equals 0. We're going to solve this differential equation. Same thing, we're going to differentiate this or integrate this. First thing I would do, I move this to the other side or subtract it from both sides. Oh, it looks difficult. How am I going to separate this? Well, with a small algebraic trick, I can separate them. I can rewrite it e to the t times e to the z. Then I'm going to bring the e to the z down here and dt to the other side. Right? So now I can rewrite e to the negative z dz equals negative e to the t dt. Integrate both sides. So the trick is to rewrite it. So it becomes negative e negative z, negative e to the t plus c. You can leave it like this or multiply by negative. Sometimes they can ask you find a solution to the given equation or differential equation y prime tangent x equals a plus y with y of pi over 3 equals a, and x is bounded from 0 to pi over 2. Okay, so y prime we can write as dy dx tangent x equals a plus y. I want to do separation, so you bring the a plus y down here and dx up there, tan x down here. I'm rewriting it. So then we integrate this, dy a plus y. For tangent x, we can write it as sine over cosine, so it's going to give me cosine over sine dx. Good. Next, the left-hand side, we can do u sub a plus y. And the same thing, right-hand side, we can do u equals sine x, so du is cosine x dx. So both of them is going to give me natural log of the absolute value of their denominators plus c. Or look, for fun, you can put natural log of c. Still constant. For the left-hand side, keep it the same. Right-hand side, you can combine them, c sine x. And we can do e both sides, which will drop the natural logs. And then when you drop the absolute values, you do plus or minus c sine x. And remember, we're solving for y, so y equals, subtract a on both sides, like that. You can replace, if you want, the plus or minus c with any value you like. They said also y of pi over 3 is a. Y of pi over 3 is a. So again, if you want, you can replace this with plus k sine x, or even c. It's fine. It's at the end constant. Again, they give us y of pi over 3 is a. So how do you use this? Y is a, and x is pi over 3. So add a to both sides. Sine pi over 3, sine 60 is root 3 over 2. Multiply by 2, divide by square root of 3, that gives me the c value. Then you can substitute this back in to get y equals negative a plus 4a over square root of 3 sine of x. Notice if you go back to the questions, it says find a solution, like a single. That's a single solution. If you leave the c, you get infinitely many. We call the general solution. So this is called particular solution. Particular solution. One more idea to talk about is called orthogonal trajectory. Orthogonal trajectories. So if you have, so notice what I talked about earlier. We have, sometimes we get a solution to a differential equation, the general solution. Notice when we have a differential equation, we get a solution. The solution was like an exponential function. Say like you had a differential equation, f prime of x equals something, and then when you solve for y, you get like ce to the x or something, right? So for every c, you're getting a curve. The curve itself is a solution to, it's not a point anymore. It's a curve. So for every c, you're getting a curve. For every c, you're getting a curve. So all these curves that you have, let's say you draw many curves, right, like as solutions. There should be one other curve or one line or whatever it is. You have one curve. That curve is perpendicular to all these solutions. Perpendicular to all of them. So this line or this curve here is the orthogonal trajectory. The word orthogonal, it means perpendicular. So if, for example, let x squared plus y squared equals r squared. Say this is a solution to one of the differential equations. Say, even if it's c squared or r squared the same. So what is this? That's a circle centered at the origin and radius is changing. For every value for r, you get a circle, right? For every value for r. So it's going to look like this. If you take a small r1, r2, or 3, it's going to look like this, right? It's going to look like this. Now, what can be an orthogonal trajectory to this? So this equation, this one has orthogonal trajectory as y equals mx. So what does that mean? M is the straight line that goes through the origin. So if you draw this one, you draw this line, you draw this line, you draw this line. So these are perpendicular. Do you see? It's going to be perpendicular all the time to these curves. Find the orthogonal trajectories of the family of curves y squared equals kx cubed. So how are we going to find that out? So the first thing, the process here, first we differentiate both sides to solve for y prime. So we get 2y y prime, that's the derivative of y squared. Derivative of x cubed is 3kx squared. From here we can solve for y prime, which is 3kx squared over 2y. But then what I want to do is to eliminate the k. So I can from there I can solve for k, which is y squared over x cubed. So if you substitute it in, 3 times y squared over x cubed times x squared over 2y. So I want to get an equation that has no k in it. So we got y prime equals, the x squared cancels, you get 3y squared over x all over 2y, which is 3y squared over 2xy, simplifies to 3y over 2x. And that would be the y prime for the actual curve. Now, the slope for the trajectory one in this case, for the trajectory, we know two lines are perpendicular. They have opposite reciprocal slopes. And remember, y prime at a point is the slope of the tangent line. So here we're going to do, for the trajectory, the y prime, we flip this and switch the sign. Flip and switch the sign. Then we can write dy dx and solve this differential equation for y. So we get 3y dy negative 2x dx. Integrate both sides, you get 3y squared over 2 equals negative 2x squared over 2 plus c. And you can simplify to get negative x squared plus c. So this one is the orthogonal trajectories for the given differential equation.